All right, so I'm requesting the Jupyter notebook from Seal for now. So because today we're gonna I think I need to show you some like demo for the smart parallel computing with Python. The homework one has been the project one has been graded. Most of you did well. I think that's good. There are some common things I think I want to point it out. One is well, quite a few of you just focus on just get a project done, which is good. Okay, that's why you're still getting like the majority of the points, but we still have some points being deducted because of the reason. One is I think some of you use the multi-processing the package from Python. I think if you come to class or watch the video, you know I've said in the class like specifically saying that's not the ideal way to implement it. You should avoid it. The reason is because the multiprocessing package from the Python library is a single node parallel computing, right? So it's a multi-threading type of thing. So if you use that, then your program will not be scaled up, cannot be scaled up. That means you can handle the project, say like using 4 processors, that's fine. But if you want to scale your program to like up to 100 processors, then that couldn't be done. So therefore, if you use multiprocessing, you most likely will have some like a few points being deducted. So that's sort of like the one of the major like common the thing. Another thing is I think is a few of the students like you have parallelized the mapping step, like the mapper step, that step being parallelized is I think it's done pretty well. But then at the reducer step, there's no parallelization. Again, for the goal of the project is to practice the map reduce, right? So it's not really about like how small the project you can use in one reducer or even one mapper to handle all the data. That'll be fine. Again, the purpose of project one, as I said, is best way to practice map reduce. So therefore, if you just if you parallelize the mapper but you didn't parallelize the reducer, that is also probably resulting a few points off. So in the following projects, okay, make sure when you're doing the project, make sure you're using the MapReduce framework. Okay, although the data set, I mean, like I said, is we have so many students, it's just impossible for us to practice on a huge data set. Like generating a data set like with several hundred gigabytes, but if we have close to 100 students to run the job on the CPU, we're going to just crash it, right? So we have to be practical. That's why the project data set is small, but then you have to use the concept, okay? The job, is not just to get the job done, get the project done, get the results. That's you can just do it without any parallel computing. That's what we try to learn here is to learn the concept. Okay, so that's a little bit of summary about the project number 1. Now, the project number 2 is coming up, which will be available to you after the class. It's already uploaded, but just setting the time. I set a time to be so you're gonna be visible to you after the class. Okay, so but I want to spend a few minutes to just go through the projects, make sure then make sure like this is clear and the project description is clear and you know what to do, what's the expectation. Now, so the project number 2, the project basically is to implement the PageRank, okay, the algorithm we learned in the class. Now, in the I generating some data sets which is under the project 2 data, so which is under this directory. It all have 10 files. Each file contains about like millions of links. Okay, so in the file, each row you're gonna see each row gonna contains 2 numbers. Okay, you don't have 2 numbers, and then those numbers are the ID for the web links. Okay, these are URL, the unique ID for the web page. So for the 2 numbers, that row is indicating there is a link. Okay, pointing from the first web link to the second web link. All right. So for example, if you have, you say this is 149, 35, 725, that means the web page with ID 149 has a link to the web page in the second 35, 725. Okay. Now, then in total, you will have 10 million links. Okay, so 10 million nodes, 10 million websites. There should be more than 10 million the links. They are probably like around like 50 million links or something. But which is a decent size, network. Okay, it's not small. It's not really that small. Because I don't want to go to like at the billions level, but at the 10 million, well, the community is still a big community. Now the requirement is using taxation methods, setting beta equal to 0.9. Okay, the beta is where, remember the taxation, the beta is the probability you're gonna follow the link, you travel through the web. And then the 0.1% you're going to use is the 10% of the probability you're going to randomly start at each step, right? So use a taxation method to calculating and report the top 10 web pages with the largest page rank values. Okay, so that's this is a requirement. This is a goal. Now requirement. This is you going to use MPI for pi on the seal for the computation, which is MPI for pi. You haven't learned it. We're gonna spend like this week. Okay, this week we're gonna introduce MPI for pi to you. So that's gonna be the main topic for for today and Wednesday. So after today, you may not be able to like today you're gonna have some basic idea for the MPI for pi. Okay, at least then you can start to think about it. Definitely after Wednesday, you're gonna learn most of those things, like even including demo for the MPI for pi. So even you have zero knowledge about MPI for before, by Wednesday you should have enough information to work on your projects. So so today, but I do want to give out to like ideally the project should be posted on Wednesday, but I do want to post like a few days earlier so you guys can start to think about the project. Okay, so because this is to do that is not just not about the parallel computing, it's including other things also. You can start planning things out. Now for the page rank, the algorithm, you only need to run 4 MapReduce iterations. Okay, you don't need to do like a 50 to 75 that much. You just need to run 4 iterations. This 4 iterations should give you enough the iteration to reach to a reasonable state, because this is a small network. Okay, so 4 iteration should be fine. So for the MapReduce, so basically you need to run like 4 MapReduce jobs. Then that should be enough. Now, for the parallel computing, you need to use 5 processors. Okay, 5 processors for the mapper, 5 processors for the reducer. However, your program should be able to run with any arbitrary number of processors. Okay, when you run it on the CWolf, use 5. But when your program, if I change your number of processors to say like 100, okay, your program should be just run 5, okay, or even like increase it to, let's say, 50 or 100. This should be not a problem, which means but which means your program should be you cannot hard code. Okay, you cannot hard code your processors. this process need to be, you need to, depending on how many processes you specify.
How does that work with Slurm batch files? Because like you predefine how many nodes. Right?
Yeah, that's the thing. If you change your Slurm file, you predefine it to the that what I mean here is
like
not
you
a
can change the Slurm file, but not the
but not your
not
no
the
program.
Okay.
Okay, so your program should be flexible enough to handle the arbitrary number of the nodes, but in the Slurm file you have to specify. That's something using 5 processors. Okay, that's now use your own directory under this folder. I noticed in project 1, some of you like created your own directory, which is part of it is my fault because I using saying this is using NetID instead of like the name. So I already created your folder, okay, in there. So just using your own folder, which is based on your last name and the first name. So under the class 2025, your last name and the first name, you should be able to you should be able to find your own folder and then store your intermediate file in here. If you have a middle name, okay, if you have middle name, the middle name will be part of the first name. Just attached there. Then that's this is a requirement, and then submission will be you need to write a report about the analysis and submit a PDF file into the Brightspace. Then the other thing is the same. Now this time your requirement it's only including like 1 script file and 1 Slurm file, okay? Because now you know you learn MPI for Pi, so you should be able to just work it out in just 1 file. Then upload your file and the script and the Slurm file to the submission directory. Okay. Again, I already created your folder in there. Just looking for it. If you cannot find it, or if you have like access issue, let me know. You don't need to go to save for the mean for the access issue because this folder I created them. So okay, I can modify them. So if you have access issue or you cannot find your name, then email me. Okay, I can help you with that. So that's this is project number 2. So any questions on the project, or is this clear?
When's it getting posted?
He's gonna post it after class. So next Monday is fall break, right? So there's no class. Then the due date I actually set in the due date will be the following Wednesday, but I think it is I'll actually give you guys an actual date. So the due date will be on the next Thursday, okay, midnight next Thursday. So you basically guys have 10 days to work on it. That should be enough. So make sure you work early, okay? You start early because in the project number 1, there are a few students like come to me in the last minute to say, oh, I don't have enough time. Can you extend it? The answer I can tell you right now is no, because this is even for project 9, you already had enough time to work on it, okay? So but the thing is you just have to start early. If you just wait to the last minute to work on it, or last like a couple of days to work on it, you will never have enough time. Okay, even I extended to like Friday to give you like 20 days, you're still gonna wait. So then the 10 days, to me, 10 days is long enough for you to finish project number 2. Okay, so that's it's so yeah, basically is I will stick to the to the due date, to the deadline. What else? Yeah, so let us know. Okay, let me or TA know what if you have any issue with it. Hopefully this is I explained the project clear enough for you guys to start think about it. All right, so let me see for my come on. It's still cute. I want to start You see, this is how it happened in the during weekend when I want to start a Jupyter notebook, it's pretty fast. But now when I want to start a Jupyter notebook now, it's become pretty. Say forever. Oh, because I want to because if I don't have this, I need to get down to the silk now. Give me 1 second. I should be. No, one thing about the Seawolf, I don't know if you guys realize it, is when you log into within the when you log into the within the login node or VLAN, the login, if you have different login node, the a queue available to you actually be different. Okay, so if you're using like a login, I think you're gonna have a different you're gonna have a different the queue. So you can using the S-info to help you getting the to find out which queue are available to you. So this should be login dot okay. Okay, so I'm coming right now. In the code, okay, the code you're gonna see is okay. Everyone see fine? Can you see? Yes. Okay. So the example you're gonna see here is in the home directory, GPFS projects. Okay. So in the home directory, you're gonna see you have I created a folder called example 2025. Okay. In here, you should have in the you're gonna see this is a the Jupyter Notebook, parallel multiprocessing. So this is we're gonna go through in just a second. And I also have a few MPI the example code, okay, just by different function. So I have a Python program and also have a corresponding Slurm file to call this Python. So you can play with it. I'm going to also show that do the demo in the class as well. But if you're interested, you can play with it or copy to your own directory to do that. I mean, just one thing is for the Slurm file, the directory is mine. So you have to be, oops. Say for the barrier, the Slurm. Okay, so this is I didn't change it, but this is my directory. So just make sure you change to your before you run it, you change to your own directory. Otherwise, you're gonna have an access issue. You can wait. Okay, you can wait until we go through them. So then that's you may have a little bit better idea how to run them. So basically, I have a hello world, the most simple, the Slurm. Then you have the send and receive for the MPI for Pi, send and receive function, scatter and gather, broadcast, and also barrier. Okay, so I have a different so like these are sort of like the main MPI processes or the functions you need to use for your project number 2. For example, you would need a barrier. Okay, you would need a barrier function in your project number 2. There's a barrier will be synchronize your program. Like you need to for the mapper being done before reducer become running. So this is you need barrier. You need problem with scatter and gather to send and receive data from the node and so on. Okay, so that's this is where. Oops. Okay, so this is the directory and our classroom directory. You're looking for example 2025. Okay, so you're gonna see this is the example is gonna be there. So today we're gonna go through is the okay, so we're gonna start to introduce. This is the MPI for Pi. Now, before I go there, I do want to spend like so the goal is to introduce MPI for Pi, but I do want to spend like a few minutes to talk a little bit about the multiprocessing, the procedure, which I think most of you, not most of you, but some of you is already know how to make it a little bit larger. You already know how to run it, how to use it. But I just probably not all of us, not all of you. Okay, so I just want to using this is just a short example, like probably like a 15 minutes introduction. Okay, so you know how to. If you want to just do a simple job, if you run the parallel job on your in a single node, this is what you can do. Plus, this is multiprocessing can be combined. Okay, can be combined with the within the MPI to speed up. MPI basically you can view it as multi-node the parallel computing. MPI is a single node parallel computing. So they can actually embed each other, so making your program even faster. So this is a so multiprocessing in Python or in Windows you can check in. This is online. I think yeah it works. So this is there's some introduction. Is very old introduction, but I think it's it can give you the because multiprocessing this package is pretty old. Okay, so it's they're covering enough for you to like to learn about like basic stuff. Okay, about how it works. Now I'll give you a couple of examples and also how do you use them. This is the first is just you just how to using the basic one. Okay, so the first of all, the package is multiprocessing. You have to import it, right? You import the multiprocessing. Then you define the two workers, worker 1 and worker 2. Being this is 2 workers, this is where your job is being done, right? The job like what you want them to do. Now in this example, the job is very simple. It's just for the worker, it's just print out the ID. And also getting is a PID, right? Process ID. So this is how this for these 2 jobs. This is very simple. So then down below, what you want to do here is just to run them, right? So this is how you define a main program. You want to run them. Then in this line, this is starting your main program. Now this is the down below. This is where the process is going to be parallel computing is going to come from. So you call the multiprocessing, the process, the function. Now you specify the target. Target, this is where the job is being specified, right? So this basically means you start a process number 1, process 1. This is just you assign a job. It hasn't been started running yet. So first you create an object, and then your target is to specify what job you want done. Then your job 1 is doing you call the function worker 1, and job 2 is for the work 2. So this is you have 2 objects that's will be set up. Then you can start. Okay, your P1.start and P2.start. So then this is where you start your processing. Now notice here, when you do this is a parallel computing, your process basically you control everything, right? You control what process, how many processes you want to start, and for each processor, what job you want to done. So you can do the very flexible way. But then the downside is that you have to specify them one by one, right? So you can start the process one by one. But you like a P1 and P2, they can actually do different job, right? That's perfectly fine. So then the main program, okay, well, wait until the P1 finish before continuing. Then you using the P1 join or P2 join. The join, this function is very is pretty important, because without join, your main program may actually finish execution and exit before the process is actually finished. If that is done, because your main program is killed, then your anything attached to it is also get killed. Okay, so in this case, you have to join them. You can just say the start and then close it. That's not how it works. So to do that, okay, so I think this is actually can run. You can just control enter, so you can see this actually being run. So you can see the ID for the main process is this guy, ID for the work 1 and work 2, these 2, and then when you call them, then this is where you print the ID for the process 1. This 2 printout is from your worker function, right? From worker function. The printout down below is from the main program. This is just show you is you actually ID for the processes. Yeah, so this basically is to run them. You don't forget you have to join. Okay, use call the join function, because otherwise, if you don't call them, the main program run actually very fast, right? You finish very fast. But you want the main program wait until all the processes like P1, P2 been finished before you close the main program. So this is sort of like one thing to notice. In the second example, we can also create the class. Okay, you can generating the multiprocessing class. You define your own class, then you start a program. So in here, you still may import a multiprocessor, but now you define your own class. You say call the process. Process, then you inherit it from the multiprocessing process, right? You inherit it from there. So then that's this is in there. You can build up your own processing. You can first you have to init it, right? Using the superclass to init it I think the SIF one, the Python, the version is still pretty old. You have to define the old fashion, but in the new one, you can just use the SIF function to define without any specified process itself in there. So this you can give the ID. Okay, basically now you can give the ID to your processor. Before you that, you kind of using the PID, right? Process ID to define your processor. But now you can actually give your own ID to each process you created. You set up then set the ID. The wrong in the wrong function in this case is you just it's very simple. You just time out for 1 second, then you do a printout. Oh, you can in the main program now you can basically say I want to create a processor with an object like the P1. I want to process a file, right? What it does is you give it an ID. So this is your input here is your ID. So that means your P1 with the ID is 5. Although I can should be 1, 2, but I just want to give a different number so you can see that. Then you can start it and join. That's also fine because it's inherited from this multiprocessor process. So inherited from that class. Then this is all the functions still be fine. You create a second one. You start and join. So you can see the printout is I'm the processor with ID 5. Now basically this is a P1 processor. Right, so that's the second one. In here, you can define if you have a class of job, like if you when you run it, okay, when you run it, you basically run the same job, right? So in this case, you can have a little bit more control by defining your own classes, you can have a little more control how your program will run. So this is a second way to do it. You can also using the pool classes for the parallel computing. So the pool class can be used for parallel execution of function for different input data. And then the multiprocessing using the pool class, then it's going to store a set of processes called workers. And then you can submit the task using the method, like using apply asynchro, and the map asynchro at all. So this is if you're using this pool method, you can run your program like in an asynchronous way. Okay, in an asynchronous way is give you like a more the flexibility in handling the data. Particularly, you have like if you have a data stream coming, this will be more flexible. So for parallel mapping, you should first finalize multiprocessor pool object. The first argument is number of workers. If not given, then the number will be equal to number of cores in the system, which is if this is a bad idea, because if you're using the core of the program equal to number of cores in the system, particularly if you run in your own laptop, that basically is gonna occupy like all the resources, computing resources, okay, which is gonna make your other program will be very, very slow. So you should always specify the number of the workers you want to do the parallel processes is somewhat less than the number of cores of the system. Right? Say your core is like 16 cores. You may want to use 8 of them for your parallel job and leave the rest 8 for the other ones. Otherwise, then for like run the system and other thing. If you don't do that, basically once your program starts, you're gonna feel your screen is freeze. It's frozen. You cannot do anything else. This is not very pleasant experience. I tried a few times, then I ignore them. Basically, have to wait until the job be finished before I can do anything else. Now, in here, I have in the pool. This is the pool class. Basically, you have import the multiprocessor. That's the same. Now I import my function. So my function is just I included in here as well in here. But my function is just basically is very simple function, just a square function. Okay, I defined it here just to give you an idea, like you can incorporate your own function using in there to make your program to be more flexible. So my function is just being your function, can be anything. Okay, in this cases, my function is a very simple square function. Now in the main program, what you do is you're gonna create a process pool, right, with 6 workers. That means your multiprocessor.pool 6. That means now your pool has 6 workers. So this operation is actually pretty close to the MPI in the sense, right? In the MPI sense, you're gonna find out the same way. you're gonna starting a set of process first, and then you're gonna assign job to them, and depending on the job, you can do different things. So in here, you basically, the first step is you're gonna start like a 6 workers. Then you can have in this results equal to pool.map my function dot square, right? My function, this is I imported this of my class, and then down there I have this square function, right? I have a square function. The square function basically is taking the input from the list. That means I'm going to square on each one of them. I have 6 workers, I have 6 input. So each one of them all go to one function. So this step basically is to distribute the work of the apply function to the apply this is my function dot square that function to each number in this list, and then you return a list of results preserved in the order. Okay, so that's this is results it's gonna do. Now once you having this, you have the results basically down below. This is you can see this is now updated, right? Around the second time the results will be basically taking the square of the numbers to each one of them. Say, I mean, if I change it to 100, right? I mean, you can just try, right? Just change this to like 100, then you run it, it's become like 10,000, right? So this is how basically this is this is a very good way to run embarrassingly parallel program in your local environment. Okay, so if you want to speed up, like you because most of the time your laptop right now this is very powerful. Or some, I mean, at minimum you should have like 16 processors. Some of you can even have 32, 64. Okay, you have a 2 CPU, so it's a pretty powerful the computer. If you can check your usage, most of the time your CPU usage is actually not at a full capacity. Okay, so you're wasting a lot of computing power. So if you run a local job, is not that big, and you think your local can handle, then using this is a pool mapping. This is actually is a very good way to speed up your computing in the local environment. Then after that, you want to close it, right? You also want to join it. Then just join again. The join function is just wait until like war workers to finish before continuing. So this is a pretty good way to implementing again the embarrassingly parallel computing. Embarrassing parallel computing basically that means for your processor, everybody doing the same thing. Okay, everybody doing the same thing. Then in the end, just to sum it up, one application to do that is to do the permutation test. Okay, I don't know if you guys heard of know this is it's called permutation. Permutation test. In statistics, this is basically is a way to generating. Say you compute you do statistical analysis. You calculate statistics, right? You calculate a result, some kind of result. But then because your model is so complicated, sometimes it's very hard to derive this theoretical distribution for the variable or the statistic you calculated. Then what you can do is you can basically the permutation test is a way to find out this empirical distribution using numerical methods. Okay, a numerical way to do it. So what you do is basically you scrum your data. Okay, you permute your data or permute your data like in a random way, and then after you permute data, you're going to use the same model to apply to the permuted data, and then you calculating the statistic you all have in one number. Okay, then you permute it another time, you got another number. So you permute it like 1,000 times, you're going to have in the variable like the statistic calculation is 1,000 times. So that 1,000 calculation essentially is your distribution of your statistics under like a null hypothesis typically. Okay, because when you scramble, when you permute your data, that means you disrupted anything like the link. Say for example, you run regression, right? Y versus X. When you permute the Y label, that means any link between your response variable Y and your input X, they will be disrupted. Okay, so which means any coefficient you calculated that is under null hypothesis, your coefficient equal to 0, beta equal to 0. So in this case, you can using this is a do this is a 1,000 times, essentially the 1,000 times identical the computation. But then at the end you summarize this 1,000 computing result together, getting a empirical distribution for the null hypothesis. And then you can use in that null distribution to determine your original data is significant or not, right? So that's you can use to calculate p-value and those things. Then this would be like using this would be a perfect way to implement that kind of the parallel, because you need to run your program 1,000 times, right? And then but each one of them is almost identical. Inside is you just input like a random function, right, to commute your y. That'll be you want a random process. So in this case, you can using this is embarrassing parallel mechanism to implement it. So this is a good way to do that. The last thing I want to point out is using the asynchronous execution. Asynchronous, that's basically when we're using the normal map function, the execution of the program is stopped until all the worker complete the task, right? So using the mapper asynchronous. This is the asynchronous results object is returned immediately without stopping the main program, and task is done in the background. So result can be retrieved by using the asynchronous results get method at any time. Now, like in here is you kind of program your if you're using this way or using this is has to be when the mapping this is mapper, like you use a poodle map, right? Then every job has to be finished before you move on to the next one. This is kind of like the map reduce, like you force them to stop. But in some cases, okay, you may not want them to be be the same, at the same time. You may want to handle them like in an asynchronous way. Asynchronous way, that's basically saying when one processor is finished its job, then you can basically move to the next one, okay? And then in this is when you do that, this is a map asynchronous way to do that. Now, when you want to use that, there are times I can give you an example. For example, if you are in a trading company, right, in a trading firm, and you want to process like the market data, you kind of receive the data stream from the like a exchange, like all the like you are doing the high frequency trading, this type of stuff. Then your server is kind of receive data continuously from like as the day goes on. You receive a lot of data from a different trading company or exchanges, right? So you're giving you fill up all the data. Sometimes the data is going to be sometimes the volume is very hard, okay? And if you want to wait until all the program, say you're starting your process like generating like a every second you process data, right? You receive data, and then if you want to wait for everybody to finish, that means if, for example, like at 1 second the data volume is particularly large, or there are some kind of like error data right in there, the cause your program like a slow down. Then if you pause, you're gonna causing delay in all the downstream process, right? If you delay for that 1 second, basically for all the downstream second, it's gonna all be delayed. So if that happens, that's what you want, because then if you delay, that basically you have a significant the lag between them, right? For those companies, they are operating like a millisecond level. There's a 1 second delay is almost like you cannot tolerate it, right? So in that case, this is the asynchronous profile would be nice. That would be good, because then you just basically, for some processes, if there's one processor is still slow, you just keep it there. But for others, if they're done, they just move on to keep working on the data. So there are cases where the synchronous parallel computing works better. There are also some cases where asynchronous the scenario works better. So this is basically called blocking or non-blocking. Synchronous the way is that's most of the time you want to do it in synchronous, because then when particularly involving like communication among the different workers, If some worker, if it hasn't finished yet, then you start to communicate, it will actually generate error. So in majority of time, okay, actually you want to synchronize your program. That means you want to run your program like a block by block, okay? So before you want to finish this is one block task first before you move on to another block. But in some special cases, you do want to use in asynchronous. That means when you parallel them, when one part of the finish, they can move on to the next phase. But when you're using the asynchronous, the parallel computing, you have to know what you are doing. Okay, you have to know what you're doing because this could be asynchronous could be dangerous. Because particularly involving like communication among different workers. So you need to be really really careful when you try to do that. In the program, like when you apply to them, right? In the multi-process way, is actually pretty simple. What you do is you input a pool and you're using pool map asynchronous, right? Asynchronous in there. So in this case, for this small example, it doesn't make any difference because the job is very fast. You cannot feel any difference. But if your job is large, then particularly involving like several steps, then the synchronous and asynchronous they make a big difference. So in this is in the asynchronous there are two things. One is using map asynchronous. That basically you're using apply the function map the function, right? Using each one of the inputs. This is to generate results. Another one is you apply the asynchronous. Using apply, then this is almost the same, but you want to use the map or map synchronous when you have a whole iterable process in a block, right? Like you have an input list. You can iterate them. You can use using the map. Apply synchronous. That's when you want your fine-grained control of your job. This is where the apply asynchronous. This is where you can apply. But you want to this is just give you the like a high level. This is I didn't even touch the details of it. Okay, this is just give you a framework. So if you haven't seen it before, if you haven't like a practice, this is a multi-process before. Spend some time, okay, to go through each example, just understand what they are. Then in the practice, you still need to like if you want to do the job, like this is my function. This is where your process your function is going to present. That's the main part. Okay, this is just give you like a framework for you to work with. There are other ways to do it well as well. I mean I don't want to spend time like talk there are probably hundreds of different ways to do the parallel computing with Python. So I just want to give a very brief way to the multiprocessing because seems like first of all a lot of you guys used it's a popular tool. Okay, it's one of the most popular tool for the parallel computing with Python, and some of you already used it, but the others didn't use it. I just want to make sure you guys know the thing it exists and how to apply it. This is although I keep saying you should using Slurm in using the COOP to do the projects. That's for the big projects, okay. But in day-to-day life, multiprocessing actually is going to be more useful in your daily job because that's in majority of the time your job is probably not going to go to the scale of the Slurm, okay. But you do have a lot of small job you can benefit from, like speed up like 4 times, 5 times using the local environment. This is where the multiprocessing is actually can come in handy. That's so I would strongly encourage you to go through this example if you haven't used the multiprocessing before, and you can start to explore them. It's worthwhile, okay, to spend like a half an hour, 1 hour to dig in this a little bit, get familiar with the processor. You're gonna making your work like more efficient, okay. All right, so any question about the multiprocessing before we Go on. All right. Now, let's back to the main topic for today is today and also the Wednesday's class is to the MPI introductory MPI with Python. Now, before we talk about the MPI for Python, we need to understand what is MPI. Okay, so MPI basically MPI is called a message passing interface. Okay, now it's a language independent communication protocol. It's not a new language. Okay, it's not a language, but it's just it's a communications protocols. Which is everybody also like agree to sending and receive data from node to node. So it's portable, platform independent, and the de facto standard for the parallel computing on distributed memory system. There are various implementations. Okay, one of these is OpenMPI, which is what we're gonna actually depend on. OpenMPI. This is free. They are sort of like people using a lot of like in the research community. There are also vendor versions, which is can include like more commercial. You can sometimes make it a little bit easier to use. This is just like you having like MATLAB, right? MATLAB you have MATLAB, which is a commercial version. You also have a free version. I forgot what's the name, like Octo something called Octo something. Or in R is the free version. They have S plus. This is the commercial version, right? So MPI, OpenMPI is the same thing. Have a free version, have like a vendor version. Linux, you also have free version. You have like Red Hat, right? You have the commercial version. This is a commercial version. They basically have more support. Okay, so that's one benefit. But in terms of the basic functions in the free version, you most has everything. Many popular software library have this parallel MPI version. You can like if you have been to taking the MS 530, MPI they're gonna be doing is they will all be using very different from this class. You're gonna probably using program like in C++, implemented using the different language. In this class, we are most of our job is done with Python, so that's why we're gonna using MPI 4Py to implement it. Now, one of the I don't know if you call it a drawback, but one of the principal not the good thing is it is challenging to design and develop program using this as a message passing. For simple jobs, it's okay. Like the job you're gonna see in this class. We don't have very complicated communication between the nodes. Like I said, it mostly is just in the sort of like a master slave type of the communication. Basically, is you're gonna having a master node, which is tell each worker to what to do, and the worker is done. They're gonna send the result back to the master node, and then you summarize it and output. So that's it. So then right, so this is like a one to many type of the communication. This is easy. Okay. Now, if you have the same, say you have 5 nodes, then if you want to do the communication, is like a one-to-one, everybody to everybody. Okay, so then in this case, it will be more complicated. MPI can handle the one. Ideally, it should be handled is using best. Its best using is actually handle the scenario down below. Okay, so you can do many to many, everybody to everybody. When it's basically when my job is done, I know exactly where my message is gonna go to, and when this is done, you're gonna send it to other, and when they receive and then information, they know how to process it. So that's more I would say smarter algorithm than this one, right? This one is kind of like the most simple way to do it. Like in 530, MSI 530, they're gonna spend like a little bit time to discuss this. They want to move on to the complicated ones. But for us, this majority of the program. This is not right for us enough, because for us we are not that communication intensive. when we talk about like later on, for the modeling part, okay, we are more like the computation intensive. So that means we want to spread the computation to each one of the node. When they do the heavy lifting, the thing is on each node to do a lot of computation. But then the final result is small. So you can send it back to the even just to one mass node. That's good enough. Okay, so so just keep in mind that MPI itself is a thing. Okay, it's a thing. It's you can do it's not a new language. It's just a protocol. Okay, it can be implemented in a different language like C++, Java, Python. R is kind of like in the last time I checked, is R has some MPI, but it's not as easy to use as Python. That's this is also one of the main reasons I cover this class with in Python. So again, as I said, MPI is not a new programming language. Okay, it's just protocol. It is a collection of functions and macros or a library that can be used in the programs written in C, C++, Fortran, and Python. Okay, you can be using using other as well, but this is the sort of like the main usage. People now is probably mostly in C++ and Python. That's how it works. Now this MPI program are based on this called SPMD model. SP it means single program multiple data, right? If we try like do the introduction in the parallel computing, this is we talk about this. That means you only have one program, you define one program, but you have many different data. So you want to apply the same program with multiple data for the calculation. So this means the same executable in a number of processors, but the input data make each copy like compute different things, right? So that's this is how it's kind of perfect for the big data analysis, because what we do is we have a big data with split into small chunks, and then you apply the same process to do the program. So this is this is how it's done. Now particularly the Pi, because we want to implement this MPI in the Python environment. Now many Python modules, okay, can actually support parallel computing. This link right here. Okay, so if you click the link, the link still works. You can see this is the parallel processing and multiprocessing in Python. There are many ways to do it. Like this is a number. I think if some of you probably already. This is for just-in-time compilation. This can speed up your program. Not really by speed up, but you can compile it in a fast way. So this is a number. This is people use it well. I also use it. Python is this is also convert your Python into C type of the compile. You can also be speed up as well. So these are the ways you can speed up. Like you have symmetric multiprocessing in here. You have different job. Then for the cluster computing, you can see MPI for Pi is just one of them, right? Where is MPI for Pi? I didn't even MPI for Pi. Okay, so here is the MPI for Pi is MPI based the solution is just one of them. Okay, there are others, right? So this is like a Celery. They have this display, DiskPy, Jog, and this is a PP. This is parallel Python. There are different ways. Okay, there are many. If you are interested in, you can check them. But to us is this is in this class what we're gonna talk is this MPI for Pi. Okay, these are like active ones. MPI for Pi is of course it's our coverage, right? So this is people use a lot. Jog, Celery, DiskPy, and PP. These are also pretty active ones you can explore. Like I said, if you're interested, you should check it. But we're gonna focus on how to using MPI for Pi. These modules. Now let's see what it is. So MPI for Pi is basically to implement the MPI in Python. It provides the bindings for MPI in Python objects, right? So in Python, this is object oriented. It's kind of more user friendly and will automatically determine many of the lead argument to MPI calls that have to be explicitly given when using other languages. Now, if you have using MPI, say using C++, okay, you're gonna know it's pretty hard to use, okay, because it has a lot of arguments, details you have to specify before you do the communication. The MPI for Pi basically is wrap up, right? It's wrap up around this is among this MPI, these functions. We make it. You're gonna use when you use it. Actually, most of details actually be hidden. Okay, it's hidden behind the thing. You don't need to use it. You don't need to worry about it. It will be you all feel it's easy to use, but you also lose a lot of the controls. Okay, you lose a lot of controls for the MPI, the details. So it comes good or bad. Okay, but for majority of the tasks we done in this class, we don't really need those details. And also plus is for people who are just want to use it, okay? You don't really need to know all the details. You just want to speed up job in a simple way. Then this MPI for Pi is farming enough. Now these are the two website which is going to give you a pretty good introduction for MPI for Pi. Now particularly this is the second one, MPI for Pi. This is a read the docs. This is a this version. So I would strongly suggest you MPI for Pi. This link right here. Okay, you can see they are giving a lot of this tutorial and a lot of examples in there. Some of the examples we see in this guide we actually borrow from this website. Now, if you here they also cover like what is MPI with Python related objects. This is actually if you want to spend some time, okay, you can learn a lot from this website. They also give you the overview, the different details on how to use them. And they actually have this is a good nice tutorial. Okay, you can run through them. We in this again in here what we cover like a small portion of MPI for Pi. Okay, so the goal for me for the MPI Pi is not to cover like all the details about it, but it's just to cover like essentials for you to get started. Okay, to explore. This is it's kind of a new word for some of you. It's if you have never used this is MPI before. This is I think this is going to open a new door for you to speed up your program significantly. Okay, particularly if you are using the like you're doing some research. I think this could be very useful. Now the execution you're going to use using this is a MPI run, which is in the CWolf. This is how you do it. MPI run you -mp. This is a number of processes you how many specify. So MPI for run this is the command. Then -mp4 that's your specify like 4 processes. Then after that, then the next is the Python program.py. This is kind of like what you regularly run the Python program. This is how you exit from command line, right? So what you do is you're just adding this MPI part component into that. But of course in your Python program you need to have the MPI for Pi. This is this component built in as well, right? Like for example in this Slurm file, you can see in one of the command, okay, is using MPI for MPI run. This is this command you run. Basically, I say I want to start the MPI process. And then I'm using 10 processors, okay, MP10. Then Python is a language I'm using, and then this is my program, and its output given to the log file. Oh, one thing I want to remind you is that when you're using the CWolf, when you load the module, you don't need to load, especially load the Python version, okay? Because in this MPI4Py, the latest, if you're using this version, once you load this, the Python environment will be automatically loaded. Which means your Python is gonna work as well. Okay, so you don't, if you load multiple Python version, the system may get confused, because if you load like the early version of the Python, like Anaconda 3, then it may create a conflicts. Okay, you may not be able to run. Also, you want to if you using this is a MPI4Py, make sure using the latest, because when you try to do module, okay, available MPI for Pi, I think. You see they have MPI for Pi 3.02, 3.03, and latest, okay? These two, I tried these two versions, doesn't seem to work, okay? So the ones works is this MPI for Pi latest. So basically, when if you want to do it, you try to follow my example. My example has been tested, so it works in the CWolf. If you try other things, it may work, okay? But because this is it's pretty, I would say it's pretty messy in there. Okay, if you change it slightly, you may create an environment where it doesn't work. Also, Slurm. I think also Slurm in the login node, you can use the Slurm 17. This version should work. So you want to module load Slurm. This is what I just want to give you guys a little bit of idea. Okay, so if you type asinfo here, this is right now I'm using login node, right? I'm using login node. Now you can see I have the short core, short 28 core, the short 40 core and other cores is not available. Okay, so these are the queues available within login node. Sometimes this will be the probably when you run the job, when you're using login node, you using some of my example, if it doesn't work, maybe because make sure using asinfo to check what are available cores. You can see here is mostly short, medium, long, large is 28 cores. Debug and this are 28 cores, right? GPU is in here. Now, and when you load the Slurm, you're using this is Slurm 17.11.12. These are the ones being given in the CWolf instruction, okay, in the CWolf instruction. Now, if I exit it, okay, if I exit it, let me open another session. Now, if you don't use that, okay, using Milan, okay, say for example, Milan.CWolf.Stoneberg.edu. This is another login node. You can go there as well, okay. So if you're choosing using this is the Milan, this will be the first time you call. Okay. So if I'm using Milan, okay, if you using this is a environment, I don't know if you can you see from the back? Is okay? Okay. I want to, I think it's setting. No, I make it a little bigger. Font, is font general. That's good. Okay, next time I'll figure out how to use it. This is control. Okay, it's hard to, oh. Okay, oh. Oh. So now if you use Milan, right? If you do module, if you want to know what is available, like in here, you can see in the Milan, in here, the Slurm is not a 17, 11, 12, that version. It's a Slurm C. If you load it, okay, you have to load this version. You have to load this version. It's different, okay? Even for the Slurm, it's different. So you make sure if you're using the login, because the reason I want to show this is because sometimes if the login is getting too busy, you want to use in the Milan. Okay, Milan, this is another login node which you can use. Now in the Milan, you load the Slurm is going to be using the Slurm C3. This version. This is a different one. Now, when you in here, you use sinfo. You can see the queues available to you are different. There's more. In here you have you have this is short 96, short 40, and then the medium 40, long 40, large 40. This has an extended debug 40. So this is more like 40 cores. Okay, so there are they have two. Basically have the C have two different sets. This is the Milan actually has more available to you. Now, for example, now if I'm going to projects examples. So if I hide areas. If I go in here, you can see what I'm using here is short 28 cores. Okay, this program will not be able to run in the Milan environment. Okay, in this login node, because if as you can see, short 28 is only available in the login node when you're using access to login node. If you access through the if you access using this is the Milan, okay, using this node to log in, the short 28 is not in here. Okay, so that's just when you try my example, just make sure you can you have to sort of like do a little bit fine adjustment, okay, to make sure your program can run. So that's this is something I want to point out because it's not the same before because I remember 2 years ago I don't see this kind of difference, but this year when I come back, my program cannot run anymore. It's kind of makes me wonder what happened, right? So this is what I found. Okay, so be sure to use. So sometimes when your program couldn't run, it's not because the program itself has an issue. It's because of the setting. Okay, the environment is different. Now the MPI4Pi module, almost all the MPI cores are supported with the MPI4Pi. It's popular in the Linux cluster and in this SciPy community. Operations are primary methods on communicators object and support communication of Pickball Python objects, and it can be optimized communication of the NumPy arrays. Now, when they do the communication, it's going to see later on, when you try to send data from one node to another node, some certain Python objects will be more efficient than others. Okay, for example, the NumPy array would be a good example to send. But if you want to use the pandas data frame, okay, then it will have some issues. So it's basically the Python object, as long as it's pickable, okay, it's pickable, then this communication should be fine. But I would just suggest you to start do using this as a NumPy array for the communication. That's usually it will be pretty efficient. Now let's skip this is because I have 2 minutes. Let's skip this. This is a little bit. So I want to show you guys so-called a minimum MPI program. This is in this program, basically in the Python script. What you want to do is from this MPI for Pi, you want to import MPI. So this is this MPI for Pi. Before you use it, you have to load it, right? You have to load it in the environment. That's where you should be done. That's in the Slurm file, right? Using that MPI for Pi. That's the environment it has to be created. So you want to load it for the MPI. Now, once you have this, you using this MPI.com communicator word. This is you create a com object, right? From here. This COM object contains like all the things like set up for the parallel computing. So these two pretty much like this is a 4 lines should be always in your script. Basically, what it does is you create a COM the communicator object, and then this is you will be carry all the communication between processors, and the get size. This function can give you say how many processors actually exist in there, and the get rank is basically tell the processors what's your ID. Okay, is getting ID. So your different process, if you want to run slightly different job, essentially is determined by the rank, because the rank is the only thing you can tell is who you are, which process you are. Your process 0 or process 10. Then you can use that to control the your sort of like a job you want to be done. Okay. So if you have time, you can go through my examples. You're gonna see some of them. It's actually is gonna be like I can show you very briefly in one of the Python script. You can see in the top lines is exactly the same. You're gonna see in there. Okay, so we're gonna talk more details next week to introduce like how to use them, give you more demos in there. If you want to start early for program 2, you can start it, but otherwise you wait until Wednesday. Okay, when you have more knowledge for the MPI 5, you can do a program 2. All right, that's all for today. I'll see you guys on Wednesday.